Thank you, and thank you for the invitation. So I will talk today about a few results with two absolutely fantastic valued students of mine. So works with Alex Cohen from the summer of 2 years ago, and a very recent result with Daniel Zhu from this summer that we're finishing up these days. And the latter one, the more recent one, will be the focus of the talk today. But first, I'll start with some general background about the objects that we're dealing with here, which are tensors, and what we mean by partition analytic rank. This is going to partially overlap with the previous talk, so I'll try to be kind of brief with the background. So the objects are tensors, which you can think of in multiple ways. You can think of them as multilinear polynomials with degree k, or you can think of them as functions from a finite dimensional vector space over a field. It's going to be a finite field throughout the talk. So k, a product, k power of that, which is linear each of the k arguments. If you name the variables, so you have k groups of variables, and every monomial has a variable, exactly one variable from each group. Okay, so that is a multilinear polynomial. For example, you have two examples of three tensors. So you can see the first one has the polynomial of degree 3 in where every monomial has one x variable, one y variable, one z variable. The second example is another tree tensor, the identity tree tensor that generalizes the identity matrix, the bilinear form associated with the identity matrix. So here it's x1, y1, z1 plus x2, y2, z2, etc. You can also think of them as higher order, higher dimensional versions of matrices. So you have a cube of numbers or a hypercube of numbers. The correspondence to the previous perspective is just collect all the coefficients and put them in this hypercube. And then another perspective, which will be very useful for us, is to think of them as polynomial maps or multilinear maps. So algebraically, what you do here is that you take one of the variable sets. So take a look at the first example with t. So maybe at the very top, you take the z variables and you take a derivative with respect to them, or you collect all the monomials to multiply z1. That's one bilinear form. Everything you multiply is z2. That's another bilinear form. So that's a way to translate a single tensor, a single multilinear form into a multilinear map, a tuple of multilinear forms. If you look at the second perspective, then what you do visually, you have your hypercube of numbers, and you just choose one of the dimensions, and you slice along. So you start with this cube of numbers, three-dimensional cube of numbers, and then you slice them into a tuple of matrices. Okay, so these are the basic objects, and they're just nicer to work with compared to general polynomials. They make the theory is kind of more neat. There's the the special case of matrices, which is well studied in linear algebra. So these are nice objects to work with. So let me define the two notions that we're talking about: so analytic rank and partition rank. So they are just a manifestation of this structure versus randomness dichotomy that you see throughout many areas of math, and then in the particular case of polynomials, or I should say tensors, this is how it looks like. These are standard definitions for structure and randomness. This is the definition, the standard definition of randomness. So what you do, you just take everything here, especially when you define analytic rank, assumes that the finite field, the underlying field is finite, because we're going to divide by the size of the finite field. We're going to average over it. So it's just a measure of bias. You fix a non-trivial additive character of your finite field, and then you just take the expectation, you sum the application of the additive character on your tensor. You just think of it as just a function here, and you sum and divide by number of summons, which is finite, and that's just going to be the size of the field to some power, and we care about the power in the negative. So that's just the analytic kind of analog of statistical distance, right? So you can think of the distribution that this function t defines. What's the probability that it takes any possible output, and you look at the distance, statistical distance between that distribution and the uniform distribution over the finite field, and this is very much closely related to the analytical, how to say a small constant, the size of the field. Another perspective, which is available to us if we talk about tensors, is that actually you can forget about additive characters, that there's a much nicer description of this. So you can intuitively you only need to measure the bias with respect to zero, not any other. So the zero element in the field is this special property if you're talking about tensors. So you're just asking what's the probability that I'm going to. So in this perspective, I'm thinking not of a tensor but of a multilinear map. So what's the probability that a uniformly random input gives me the zero vector as the output? The tuple is the zero tuple, normalized with logarithmically. Basic facts. So makes sense as a notion of rank. It's always between 0 and n is the dimension of n is the number of variables in each group. So you should think of analytic rank 0 is precisely when your tensor is the zero tensor, when the coefficients are 0, but generally speaking, a small analytic rank means that the tensor is the distribution, the output distribution of the tensor is biased. There's a bias specific towards 0. And whereas if the analytic rank is large, goes with n, then we're talking about a random looking function or tensor. As an example, it's not hard to compute that the analytic rank of the identity tensor, and this is the identity tree tensor. And so you just get something which is q to the minus n, q is the size of the field, so the analytic rank, so that would be that probability that you're going to end up with the 0 as the output, so that means that the analytic rank is essentially n. Yeah, the set analytic rank of the tensor is 0. So that's the measure of randomness. What is the measure of structure that we're dealing with? So partition rank, that would be the standard name for it. It's just the minimum number of partition rank 1 tensors that sum up to our tensor, or you can think of that as the number of reducible tensors. Reducible just means as a polynomial, it's not irreducible. You can write it as a product of two lower degree polynomials in a non-trivial way. And how many reducible tensors do you need to get your own tensor? I'm writing the same thing again here. Notice that if I want to be more explicit, each reducible tensor is a product of two lower order tensors in disjoint non-empty disjoint variable sets. Okay, so here's an example for reducible tensor, reducible polynomial. It's not hard to show that the partition rank is also between 0 and n. And again, it's close to 0 means highly structured. Close to n means there's no useful algebraic structure there. And okay, you can see, if you want to see the upper bound, you can always do what we did at the beginning in the first slide. Look at anything that multiplies z1. The zi's are one of the variable sets. Everything that multiplies zi, everything that multiplies z2, z1, z2, etc. So you have n variable and z variables. And each summit here is a product, right? Reducible tensor. Okay, cool. So maybe the most fundamental question about structure versus randomness is what is the relationship between structure with randomness here defined as analytic and partition rank, our objects are tensors. So k over 2, k equals 2, so we're talking about 2 tensors now. Actually, analytic and partition rank are just the same as the usual notion of matrix rank. That's easy enough to see, but if you just look at the probability that you get 0 for a uniformly random input, then this is just the normalized size of the kernel when you view T as a map, as a linear map in this case. And then you just use the ranknarity theorem. And you just get exactly q to the minus rank. So you take the logs and you get that the analytic rank is the same as matrix rank, is the same as partition. Okay. So one direction is actually easy. So it's always true, no matter which tensor we're talking about, of which order, the analytic rank is always smaller, bounded from below, from above by the partition rank. This is known. It's not hard to prove. I'll skip the proof here, but it's like a three-line proof. The real question, which is maybe the gist of the structure versus randomness dichotomy, always is the other direction, which intuitively says that if your object, your tensor, exhibits some bias, there has to be one explanation for that. It has to be because there is some global algebraic structure to your object. There's no other reason. There's no other way to be biased. So Green and Tau phrase this way, or maybe for polynomials, Green and Tau, it's the same influential paper that was mentioned in the previous talk. Green and Tau gave some quantitative bounds. So they showed that yes, there is a way to bound the partition rank in terms of the analytic rank, and k, which we think of k, the order of the tensor, as something fixed. So you bound the partition rank only in terms of the analytic rank, independently of the field size, more importantly, independent of the number of variables. Okay, so in everything here, and in most of the applications, we think of the number of variables as being unboundedly large. Okay. So their proof used the
depending on the field size. I think it's Shahar.
Right, yeah, thank you. So the original proof did have some dependence on the field size, but then there was some later refinements by Kaufman and Ovet, which again was mentioned in the previous talk, and Baruch and Ovet, that got rid of that assumption. Thank you. The bounds, though, in those refinements are the same bounds. So these three works all use the kind of underlying all three is the same kind of regularity type arguments for polynomials or tensors, which is very inefficient. So the bound that you get here is common type growth. She mentioned that actually a similar problem was already looked at in the number theory, in the context of number theory by Schmidt and maybe even before him. The difference here would be that those results actually did have a dependence on the number of variables, which we do not want. In terms of applications, there's plenty of them, in all kinds of areas. It shouldn't be, so maybe I shouldn't say applications per se, but it's used in. So this kind of inequality, either for tensors or the closely related analog for polynomials, is the component in many applications in many areas. The recent famous proof of Stillman's conjecture in commutative algebra, it's very important in the context of higher order Fourier analysis. A lot more. And again, that shouldn't be surprising because this is just the concrete way to talk about structure versus randomness when your objects are polynomials or tensors. Problem is that all of the applications inherit the same bound from, if you use the Green and Tau result or the refinements, they all inherit these Ackermann type bounds. And so all of these applications that you get are quantitative, right? There's no nice bounds if you use the Green and Tau theorem, but so that's a good motivation to try to improve the dependency, something more reasonable. So actually for k equals 3 and even 4, there were specific works that dealt with those cases, and actually they prove much better bounds. As you can see, it seems like for 3 and 4, some head-up analysis gives you polynomial bound. But the big question remained, what happens for K tensors, right? Is there a polynomial bound of the partition rank in terms of the analytic rank for any K? So that was the big question, and there was these two breakthroughs results by Moshkovitz here and Yanzer, and they indeed proved that. So they bounded the partition over any finite field for any K. Partition rank is bounded by the analytic rank raised to some quantity that depends only on K. It's a pretty scary quantity, but at least we know that there's a polynomial relationship, so that's excellent. Or at least it's definitely much better than the previous situation. But multiple authors have wondered, actually, maybe structural randomness are the same absolute constant. Maybe it's actually the case that partition rank, well, we know that partition rank is always at least analytic rank. Maybe it's always bounded by some constant times analytic rank. So they're the same quantity up to an absolute constant, or constant that depends only on K. It's a very bold conjecture. And if true, if proven, this would kind of complete a long line of works, which maybe you can say goes back to the 80s. So that's a very broad conjecture and would be very useful in all the applications. For example, some of the applications would maybe iterate this bound, and so it's really important to get the right bound between partition and analytic rank. So there have been some recent cracks in this parallel. So for K equals 3, this conjecture was shown. So this is the first paper with Alex, and also independently Abiposito, Kashdan, and Ziegler here, prove that partition rank is equal to analytic rank up to a constant for 3 tensors specifically. Mendel also mentioned that an important component here is a paper by Bergson, and I think we will hear about that paper tomorrow. But what about K tensors? So that's the topic of the second work with Alex. So we're also able to obtain a very good bound. In some sense, the constant here is the right constant. For any K, there's a big caveat though here, which is we need the field size to be large. How large? How large means independently of n. Okay, the number of variables can still go, the number of variables can still be a billion, million, but gazillion, but then the field size has to be large in terms of the analytic rank. So you might wonder, well, is that really useful? So one way to defend this is to say, well, if in your application of the partition analytic rank inequality, in your own application, analytic rank is large, and by large I mean goes with n, then we know from the easy direction of partition versus analytic rank that partition rank is at least analytic rank. So your partition rank also goes with n. So that case is not the interesting case. So really what we're left with is the case when analytic rank doesn't go with n. That means that our assumption on the field size also doesn't go with n. So it's some quantity that doesn't go to infinity. So maybe it's not that this assumption is not that bad in this sense, but it might not. This kind of argument might not be very confusing if not very convincing if what you care about is F2, the binary field, or F3. Okay, so none of what I said is very helpful in that case. Let me just quickly mention some main ideas here. So we use algebraic geometry here and use kind of we look at relevant varieties and we analyze them using tangent spaces, and we use tangent spaces to construct the partition rank decomposition. So in that sense, it's a local analysis. We're going to look at tangents at a particular point, which point that actually is a big issue, but I'll say something about that in a moment. And that's different from previous results, previous proofs that use combinatorics, or more global, more difficult analysis. Maybe what I want to say here is that this result picks a point on a variety that corresponds to T, which needs to be, for the entire analysis to work, the point has to be an F rational point with coordinates in the base field. And it also needs to be a non-singular point on the variety. And to guarantee that, maybe other properties for kind of essentially a general variety, that's problematic. So we did have this iterative construction of subvariety. So we start from kind of an arbitrary, almost arbitrary variety, and you find some subvariety that retains all the F rational points and has a point which is also F rational and non-singular. But that requires a lot of work and kind of is responsible for the assumption on the field size. So it completely breaks down if your field is small, which maybe is not surprising. But then there's another lemma in that paper. Yeah.
Is there a polynomial bound that is not depending on the field size?
So the Milošević and younger one, this.
Okay, but with a kind of bad, okay. Like I was thinking more like degree K or something.
So until now, no, but the answer is yes if you wait a few more minutes.
Oh, okay.
Okay. So okay, and so another lemma in this paper is that maybe that's a second defense of why the assumption on the field size isn't that horrible. The horrible thing to have, even if you care only about small fields, which is actually, so we prove this, I don't know, I call it a field extension lemma, saying that if you can prove this inverse conjecture, this partition rank analytic rank conjecture for field size, for any field of size, which is, sub-exponential in the analytic rank, then actually you basically prove the actual conjecture. Then you can show that for any finite field, the partition rank is bounded in terms of the analytic rank to not to the power of 1, but 1 plus little of 1. The little of 1 goes down in the analytic rank. So the proof here, well, it's not very hard. You look at an extension of your ground finite field, and you fix the basis and you analyze what happens to the partition rank and the analytic rank over the extension, and you try to relate the partition rank over the original field and the extension, and same for the analytic rank, and you can show this bound. So the first bound is not hard. The second bound uses the subadditivity of analytic rank, which is some approximate version of it proved by Gauss and Wolf, but the true subadditivity was shown by Lovett more recently. And then if you just combine these relations, then you start from partition rank over F, you lift to the extension, and then you relate it back down to the analytic rank over the ground field. And in this process, you can lose a factor that depends on the degree of extension. But if the degree of extension only depends sub-exponentially on the analytic rank, then this term is, not kind of negligible compared to the analytic rank. So that would be great. Unfortunately, our proof, right, that I mentioned before, inherently, right, because we're using algebraic geometry, inherently we have these double exponential bounds. So we don't get the sub-exponential bound on the field size. We actually need the field size to be doubly exponential in the analytic rank. So that's not much. And this field extension lemma is nice. It shows that maybe if you can prove the conjecture under some assumption on the field size, that the field size is large in terms of the analytic rank, but as long as that size is not double exponential, as long as it's slightly sub-exponential, that would kind of almost settle the entire conjecture. So that brings me to a very recent work with Daniel and Joe, where we actually are able to do that. So we prove for any k tensor over any finite field, say the binary field, that the partition rank is bounded by the analytic rank times the polylogarithmic factor. Okay. So from now on, for the rest of the talk, let me give some taste of the proof. Some main ideas here is that one is that we define this Cohen analog of this geometric notion of a generic point or a non-singular point So essentially there's no geometry in our proof, which is key here. Everything is combinatorial, everything is probabilistic, but nothing geometric here, except maybe some intuition. Another important concept is we define a new notion of rank, which we call local rank, but that's actually a vector. So it's not, as opposed to other notions of rank, it's not a single integer, but it's actually a vector of integers. But it actually turns out that it serves as a bridge between an analytic rank and position rank, and very, very intuitively, I'm slightly lying here, but you can think of it as the kind of the infinity norm of this vector of this local rank, lower bounds the analytic rank, and the L1 norm or weighted L1 norm of that vector is an upper bound of the partition rank. So this vector kind of serves as the bridge between these the quantities partition rank and analytic. Okay, so let me kind of define for you this local rank definition. This applies for NK, and it might seem like a slightly scary definition, but it's not that bad, and it turns out that it's exactly what we need. So let me try to be brief here. So from the rest of the talk, I'll stick to the perspective that the tensor is a D-linear map. So D would be k minus 1 in the previous notation. So again, it's a tuple of multilinear polynomials. And let me denote by z of t the zero set, so all the inputs that get mapped to the zero vector. This is all, so V is a vector space over the ground field. So z of t is a zero set, it's not an algebraic variety, right? It is not happening over the algebraic closure of F. This is all happening on the base field. We never stray from that, essentially. Okay, so let me define some terminology. The partial metric. So if you take your tensor, and let's say you fix a point, right? Every point has the components, right? And you fix an index. Then you can think of your D-linear map. You can think of it as a matrix if what you do is you plug in the point X, except in the I coordinate, you just leave it as a free variable set. Okay, so that means you plug in something into all but one of the variable sets. So that means instead of a D-linear map, I have a one linear map, aka a matrix. So this would be, I call that a partial matrix. So, and you can do that, but you can do that for any point X, and you can do that along any dimension. So those are plenty of ways to think of a tensor as a matrix. Of course, this matrix alone is not enough to, it's a very limited view of the whole tensor, but we actually show that we intuitively can kind of combine all these limited views to get partition and composition to actually analyze the tensor as a whole. Another way to think of it is very similar to what I did in the first slide. You start with your linear map, and for each polynomial, you take its gradient with respect to one of the variable sets, right? So in each of the components of the map, this polynomial, I replace it with a vector of polynomials. So now you have a tuple of vectors, so that's a matrix. Let's think of it. Oops, there we go. Okay, good. We can think of it as if you have another view of that. You have a matrix, so it's two-dimensional, but every entry is a polynomial. It's a d-1 linear form, so it's a matrix of polynomials and evaluated at that point x, which I don't care about the ith component, but otherwise it's evaluated at x. Okay, and I don't know. Let's call partial rank the rank of a matrix like that. Okay, so what can we do with these partial ranks? Can they be enough to teach us a lot about the tensor? So let me now define this local rank. Slightly scary, but okay, let me do it slowly. So first we need to define this notion of an adjoint pair. That's the name we came up with. So suppose you have 2 points now, P and X. So we have these d-1 conditions where, so we look at d-1 points that I denote them as P concatenation I X. So by which I mean the point that the points that start P1, P2. So the first I component of this point come from P, and the rest come from X. Okay, so if I equals 1, so I get P1, and then the rest are X's. I equals 2, P1, P2, and the rest are X's. So forth. So I have D minus 1 points here, and I require that all of these D minus 1 points be in the 0 set. Be in the 0 set of T. Maybe it's worth remarking that P sub D, the last component of P and the first component of X, that don't actually make an appearance here. So you actually can replace the index D here with D minus 1, but never mind that. And here's the main definition, local rank. So we have a tensor, it's a notion kind of notion of rank of a tensor at a point. So it's very important that you also specify a particular point. Over, in this case, the base here. So what do you do? So let me walk you through this expression. So what you look at, let's look at the last coordinate of this vector. So you have this partial matrix where here, right, we had concatenation sub D. So you take all the D components of P and nothing of X. So just this partial matrix is just T evaluated P when you forget the last coordinate. So certain matrix, you can look at its rank, fine, you get something. Now the rest of the D minus 1 coordinates, you plug in these points. Okay, so for example, you plug in this point. So in a sense, you peel off the last component, the P sub D, and you plug in some X, the D component of X, and then you forget about the D minus 1 component. So you get another matrix and the rank of that, and you keep doing this. You gradually peel off a component of P until you're left with one component of P, but then you forget about that component. So you get something that doesn't depend at all on P. Okay, so this is a vector of ranks, a vector of partial ranks. What do you do with this vector? So it depends on X. I'm going to maximize over all choices of X that are adjoint to P. So all choices of X that satisfy these D minus 1 conditions. Okay, bear with me. Last item here is that I'm maximizing a vector. What do I mean by maximizing over a set of vectors? So I need to order them. So the right order here turns out to be lexicographic order. So what does it? So I'm taking the X that gives me the largest vector in lexicographic order. What is lexicographic order? So when you compare two tuples, you first compare their last coordinate. Whichever tuple has the larger coordinates, that's the larger tuple. If they're equal in that coordinate, then you go back and compare again. So it has a very recursive definition. Okay, that's it. That's the definition of local rank, and turns out that this is what it is. I can give you some examples. So if you local rank of the 0 tensor at any point is obviously it's not hard to see that all the partial matrices are just the 0 matrices, and so you get a vector of zeros. And maybe if I look at the identity tensor, the n by n by n, so forth, the identity tensor, it's actually a bit tricky to analyze the local rank because it very much depends on which point you're talking about. But if I make my life easy and just choose the point P to be any point where the first component is the 0 vector, then it's not hard to see that all the components except the first are just 0. You can take me at my own, but it's easy to check. And the last coordinate also not hard to see since, well, it's not hard to see the last coordinate. You actually have a maximization since all the coordinates here are fixed. Then maximizing over the vectors is actually just a one-dimensional maximization of the first coordinate. The first coordinate turns out to be n. The take-home message here is that this will not be something that I would consider a small local rank, because this is a vector. So what do I mean by small? But it has a component that goes with n, so that's kind of relatively high local rank. Okay. So you can think of this complicated definition as some kind of a far-reaching generalization of what's known as a commutative rank. So what is commutative rank? This is, it's defined for maybe either a subspace of matrices, or maybe I should say it as a single matrix where every entry is a linear form. And the commutative rank is just the maximum of the rank of this matrix, or where you take the maximum is over all choices of inputs. Okay, so you take the input to the forms that would maximize the rank of the resulting matrix. Okay, so that's commutative rank. And let me kind of convince you that local rank is very much related to commutative rank, at least for tensors or bilinear maps. So if we fix D to B2, so now we're talking about bilinear map. Okay, let me go quickly over that. The point is that now the partial matrices are just matrices of linear forms. Now I have two partial matrices, one for each dimension, and they're both linear. Every entry is a linear form. And the adjointness condition, right, there were D-1 conditions, but these two now, so that's just one condition. And I'm identifying U and V as elements of V instead of V squared, because I said that you can forget about the one of the coordinates, it doesn't play a role. And then if you look at the local rank, the definition of the local rank, so as always, the last component is fixed once you fix the point that you're working with. And so you only have one coordinate instead of two coordinates. And so they call it, so again, it's a one-dimensional maximization. So I can forget about the second coordinate, and I can just push the maximization onto just the rank. And so you take the maximum of the rank of a linear matrix, which is exactly commutative rank, except for us, we're not maximizing over every possible input to the linear matrix, but rather only inputs that are already zeros, already in the kernel of the other partial matrix, defined by you. Okay, so it's kind of a commutative rank of a restriction of T. Okay, but so that's for 3 tensors. For 4 tensors, it looks kind of different, but you can think of it kind of as a generalization of commutative rank. Okay, so let me talk about some main ideas in the proof in the time that I have left. Okay, so I need two more notation, and I can state the main components of the proof. So I want to have a norm that I work with throughout, the norms for these rank vectors. So I'm going to choose the L1 norm, but just weighted exponentially, which will be needed soon. Think of it as the L1 norm of the vector. And here's an important definition. We call a point P generic, or for lack of a better term, I say generic, singular if the local rank of the tensor T, so this is generic for given T. The local rank of T at the point P is the same as the local rank over the algebraic closure. So what do I mean? So what is this local rank bar? So you view T as an element or as a tensor over the algebraic closure. Okay, so that means that in the definition of local rank stays the same, except now you maximize, right? You maximize over an infinite, like an infinite vector space, right? The x's come from V to the D, and V is now over the algebraic closure. So there's a particular difference. So you can think of a generic point as a point where the fact that I'm, when I define local rank, the fact that I'm maximizing only over the ground field, only over access from the ground field, it doesn't matter. That the ground field is rich enough to capture the local rank over any field extension, over the algebraic closure. So that's the main point here. And that's kind of the replacement, in some sense, of what we had in algebraic geometric proof with Alex, where we wanted a point that's non-singular on a variety, which is f-rational. So this is the kind of the combinatorial analog of the same of that thing. You can think of it like that, but there's nothing geometric. Okay. So here are the two components together finish the proof. So first, if we can show that as long as you take a generic point, we can always bound the partition rank in terms of the norm of the local rank. So that's one step, one half of the proof. Proof here is sorry, I'll talk more about it, but basically it's algebra with determinants. We're building a formula using determinants. The other half is in the other direction. So we bound from above the norm of the local rank at a generic point. Oh, maybe I should say the other way around. Assuming that the field is large enough, we can show that there is a generic point in our sense. And moreover, the local rank at that generic point is bounded in terms of the analytic. And the proof here, again, no geometry, it's only probabilistic argument, analyzing a certain random walk. The important part here is that the assumption to get a generic point, I need the field to be large, and large here still means depending on the analytic rank. So kind of like the similar problem as we did this work with Alex, except now I don't have a double exponential dependence. It's a polynomial dependence on analytic rank, which is perfect, right? Because for the field extension lemma, I needed the sub-exponential dependence, and I would be done. Here I get the polynomial dependence, which actually translates into this polylogarithmic term. So it's not just, the final result is not just the partition is bounded by analytic rank to the power of 1 plus liter over 1, but actually that liter over 1 is just polylogarithmic. Okay, so if I prove these two things, then I'm done. So let me say a few sentences about each part. So the main idea in the first part, where I'm bounding the partition rank in terms of the local rank, is that we actually prove a stronger claim. We actually essentially build one rational map, one formula that given a point P and given a rank or local rank R, I'm constructing one rational map that does the trick for all tensors with local rank bounded by R, P. And this is a rational map, so it might not be defined over well. So for it to be defined, I need the local rank of the tensors to be exactly equal to R. So it works for this set, but it's defined for that. So I'll show you an example, and it will make this much clearer, this kind of statement. Importantly, here we're talking about algebraic closure for the formula to work, and for it to be defined, it's not that, it's the version of local rank without algebraic closure. But if the point P is a generic point, then this distinction doesn't matter, and we're kind of done. We just choose R to be the local rank of our tensor and just use the formula. So let me give you an example. So this is proved by induction. So let me talk about the base of this induction, and this should give you a sense of what am I talking here about. So for D equals 1, so we're talking about one linear map, so linear maps. How would such a rational map look like? So first, let me start, like show D to remind you this simple formula from linear algebra, that if you have an invertible matrix, you can always express it as the aggregate matrix, okay? So that's a matrix of determinants normalized by the determinant. I use this equivalent sign just to mean that if you take common denominators, then it's actually an equality, polynomial equality. So the aggregate matrix is the inverse times the determinant. Okay, that's linear algebra, should be believable. Okay, what happens if I take this equation? Again, once I have a common denominator, it's a standard equation. Now it's a usual equality. Now I multiply both sides on the left by A and on the right by A. So what do I get? Here I get A adjoint A times A, right? Divided by this number, determinant. And on the right hand side, I get A times A minus 1 times A. So I get A back again. So I get this formula. Okay, but actually, this is the kind of thing that I want, because I express, if you ignore the denominator of this number, A, I express it as a product of, say, two matrices, the matrix itself, A, times this other matrix. So So this is actually a factorization of the matrix. But the factorization of the matrix is precisely gives me a rank decomposition or partition rank decomposition. Why? Because you can take the first column of A and the first row of this other matrix. Take the outer product, multiply them. So it's outer product of two vectors. Plus second column of A, second row of this other matrix. And go on. And this is exactly what we mean by partition rank decomposition. And in fact, every entry of this partition rank decomposition is in particular, this matrix is polynomial in the original entries of the matrix. So just determinants. That's absolutely great. What's the caveat here is that for this to work, you need the matrix to be invertible, right? Or in other words, but for this to be, I should say, for this to be defined, you need the determinant to be non-zero. Otherwise, you divide by 0. By the way, this actually works for any matrix. For any matrix, n by n matrix of rank at most n. So any matrix, that's because, like, if you take a common denominator, if the matrix is not invertible, then the determinant is 0, and here you also get 0. So you get 0 equals 0, and this works. So this works for any matrix, and by which I mean the equality applies to any matrix, but the equality is defined, the determinant, the denominator is not 0, if the matrix has rank n. And it can be shown, this we also did in the paper with Alex, that this can be extended not just to invertible matrices of rank n, but matrices of any rank. So this is the formula that you get. Just take the adjugate of some R by R submatrix with the caveat that I need to look at all the R by R submatrices, all the choices of R rows and R columns. Okay. That's why I did the plural rational maps, not necessarily a single rational map, because you might, you get a bunch of equations here, but maybe one of them applies to your particular matrix. But this is exactly the kind of thing, this is exactly the case D equals 1 of this general statement, right? Because this general statement is about the local rank, which for D equals 1, this is just the usual matrix rank. The point P doesn't matter doesn't make an appearance in the definition of rank, and the algebraic closures also don't matter if we talk about rank. And that's exactly what I want. That this thing is defined for any matrix. So this is an equality for any matrix of rank at most R, and it's defined for any matrix of rank exactly R. So where the determinant of sums R by R minor is non-zero. Okay, what do we do about, to prove by induction, what do we do about the next case or the induction step? So the formula kind of looks like that. It's a bit opaque, so maybe that's too much to talk about here, but very, very intuitively, what I do here is that I also use adjugate matrices to construct this polynomial map that gives me a projection matrix onto the kernel, and kind of I decompose my tensor into, or I should say, I decompose the last component of my tensor inductively into those assignments that would put me, on this in this kernel and or its complement or its orthogonal complement. For the latter, I can bound the rank. The orthogonal component, the orthogonal complement here of the kernel would have, rank which is bounded by the definition of local rank, and the other component that I can deal with inductively. So then there I use the rational map from the induction hypothesis with kind of the right R. So anyway, it's a bit much to go into here, but I'll just say that if you do that, then at first it's not too hard to show that this gives you back this kind of applying this doesn't do anything if the matrix is rank at most R1 here, and if you sum them up, you get back your original tensor, or I shouldn't say original tensor, you get back this linear matrix. And in terms of the partition rank of this formula, the number of summons here, so this has R2 summons, this has R1 summons, but so this gives me a formula for this linear matrix. If I want to get a formula for the actual tensor, for the actual for the original map, then what I need to do is to take the gradient takes the derivative with respect to this last component, and it should do that at a point that maximizes. So that ties back to the definition of local rank. And by taking the gradient, that means that the first term is now double. The partition rank is double. Long story short, if you just kind of stare at it for a few hours, you can probably convince yourself that the definition of local rank is exactly what you need to make this formula work inductively. So to make the induction step work, you exactly need all the features of local rank. Okay, the fact that you have lexicographic ordering, the fact that you maximize over ranks. So this is kind of the reason why we define local rank the way we define it. I should also mention that this D equals 2 case, this more agrees with what we did in the previous paper for 3 tensors. But that paper doesn't work for 4 tensors, this does. Okay, and maybe let me say something about the second half of the proof. Maybe last 5 minutes. That we can bound the norm of the local rank by the analytic rank times a constant. So this is a purely probabilistic argument. So what we define is a random version of local rank. So the local rank maximized over all possible x's, what are joint x's. And here we're taking the random choice of x, except the random choice of x. So it has to be an x which is a joint to the point P. A random choice here wouldn't be a uniformly random choice, but it has to be kind of in a dependent way sampled. Specifically, we kind of do it step by step, each time uniformly choosing the component. So we start with the point P and then kind of renormalize uniformly choose the last component and the one before that, and so on and so forth. So it's important that we choose X in that way. And also we need, for the analysis, we need to, since we need to analyze local rank, which is about colexicographic ordering, then we define a probabilistic version of colexicographic ordering, where you compare you don't compare tuples, you compare random variables, tuples or random tuples. And maybe the key lemma here is that the key connection between local rank and analytic rank is this connection between partial ranks and analytic rank. So it turns out that if you take a partial rank in any dimension, for any I, you take a partial rank at a random point in the 0 set, then the expectation is always bounded by the analytic rank. That's somewhat interesting in the sense that it's important that you take a uniformly random input from the 0 set and not a truly uniformly random Z from the entire vector space, because then actually you can show that the reverse inequality holds, and that the reverse inequality can actually be very much reversed in the sense that if I make this change and I don't choose, if I choose the uniformly random from the entire space, then the left-hand side can be N and the right-hand side can be Z. So this is the key connection between analytic rank and partial ranks, and our goal is to leave this into a statement about this local rank, which is a vector of partial ranks. That requires some work. In particular, we use a bit of algebraic geometry here, in the sense that we need to look at all the tensors whose local rank or the closure is at most some vector R for any given R. Turns out that this is a variety. You could show that this is a variety. You can write down equations for it, and in fact, the equations only depend on R. So that's useful. And the reason it's useful is because we're later going to look at a subspace of tensors that many of them, so a large fraction of that linear subspace of tensors has this local rank. But the thing is that a linear subspace can't intersect a variety in a large proportion if the variety can be defined by polynomials of low degree, assuming that the field is large enough. That just follows from Schwarzenberg. Okay, okay, I'll skip kind of the steps here. running out of time, but bottom line, we analyze, we define this. We take a linearity of expectation, and by averaging, we find the point that we need that satisfies the properties. Then we need to use. We know that the expectation is bounded, so we might want to use a Markov inequality, except we want to stick with vectors. And Markov inequality is a statement about random real numbers, positive real numbers. So when we kind of define this, we have this pooling lemma, this kind of lexicographic Markov inequality. That's where we stay in the we still talk about it. We stay with the language of tuples instead of reducing to numbers, instead of just looking at the norms. Then I use this defining degree lemma and use the assumption of the field size. Combining this all together, we get our result, assuming that the field size is larger than this quantity, but this quantity again depends on R, and it can be related. So this product can be related to the sum, the weighted sum of the RIs, but the arithmetic geometric means inequality. And if you do it carefully, you get exactly the assumption that I mentioned before. And that's it. I'll stop here.
Are there any questions?
So is there any hope that the actual second part of the proof works in any field?
Is there any hope that this one would work over any field? It's a good question. I'm a bit doubtful.
Okay.
I'm a bit doubtful, but maybe, no, I'm a bit doubtful. I don't think so.
So here's a naive question. Suppose that you have some restriction closed properties of k-dimensional tensors. And you know that dimension n, that is the first time that you see tensors that do not satisfy this. Could it be that the partition rank is linearly bounded by some constant times n?
I mean, using this relationship with.
Well, I don't know. So in other words, so here you use analytic rank being small implies, and
right.
You show that it implies partition rank being small. Could it be that basically any property being small, so the first n where the analytic rank is bigger than R, is I guess R or R plus 1 or something. So.
Do you know something like this? I mean, something like this would
So
from
polynomial, I think it is true. So
you
if replace linear by polynomial, I think we know it is true. But,
so I guess if the proof of that relies on the relationship between partition rank and analytic rank, no. Oh, it doesn't.
no, there's no.
I see. Oh, then I'm not sure. I like to think. Good question.
So the proof is completely different from the previous proof.
Yes. What I should say that the first part of the proof is where we construct this formula. That's kind of similar to what we did with the paper with Alex. Okay. But it's much more general, and the second half of the second claim is completely new.
Questions? If not, let's thank you again.